Okay, so in this module we're going to get into graphing polar equations. All right, so let's start with just basic polar equations where we have r equal to some constant value. Let's say r equal to, let's say 3. All right. Now, if you notice here, what you see is there's no value for theta. All right. So that means that whatever value theta takes on, right, one thing that has to remain the same is that r is equal to 3. All right. That is our rule, our equation essentially. What can theta be? Well, theta can be really any angle. Right. So if we think of, okay, well, if we're graphing here on our polar axis, 1, 2, 3. All right. So when theta is 0, the value of r is 3. When theta is, I kind of lock myself in here. 1, 2, 3. When theta is, let's say, pi over 2, the value of r is 3. When theta is, let's say, pi, the value is also 3. Right? So that distance from the pole is also 3. Right? In other words, what we have here is the equation of a circle. And we can imagine that's a nice, perfect circle there. Okay, so whenever we have some equation where r is equal to some constant, then we know we have the equation of a circle. Now, it's not going to matter that the value of this is negative either, right? So let's say that we had r equals to, let's say, negative 2. Right, so if we have here our pole and our polar axis, when theta is 0, the value is negative 2. So it wouldn't be this point, it would actually be the point out here, right? And when theta is, let's say, pi over 2, the value is negative 2. Again, not the point up here, but the point out here, right? Reflected across the pole. Right? And when it's 3 pi over 2, the value would be negative 2. Again, reflected across the pole. Right? And when the value is pi, negative 2, it would be this point. Again, all if we continue doing this, right, we can see, all right, all that is required is that it is 2 units from the pole. So again, now we have the equation of a circle. Right, so regardless of whether it is a positive or a negative value, if we simply have an equation r equals, right, then in that case we're always going to have r equals some constant, then we're always going to have a circle. Right? Well, now let's look at the other case, right? What if we have theta is equal to some constant? Let's say theta is equal to pi over 3. All right. Now again here, the only requirement here, our rule, our equation, is that theta is pi over 3. So what can r be? R can be any value. All right. So all that's required is, let's say this here is pi over 3. Right. R could be, let's say it's 1. All right. Well, as long as the angle is pi over 3. Right? Let's say it's 2. Right. Let's say that's somewhere out here. Right. Or even negative values. So those would be somewhere out there, as long as we still have just simply pi over 3. Well, that means that we have here all of these points along the line. Right? Those are always going to have that reference angle of pi over 3. Okay, so regardless of what that theta happens to be, right? If it's simply theta equals to some constant, what we have there is a equation of a line that goes to the pole, right, or the origin. Okay, so now what if we had something a little more interesting? Right? Let's say we had a function of theta, right? Now, in most of our examples here, I think just about all of them, right, we're going to take the formulation where r is equal to some function of theta. Right? So we're going to take that approach here. Okay. So let's say we want to graph something like this. R is equal to sine of theta. All right. Now, what I'm going to do is I'm going to graph in the r-theta plane. This is a rectangular system, similar to our xy plane. Right. So here, all right, and I'm going to graph one cycle here. Of r is equal to sine of theta, right? Again, our theta plane, if we have this formulation, we think of our theta as the independent variable and the value of our r as our dependent variable. Okay, so we start off at 0, reaches a height of 1 at pi over 2, then 0 at pi, and I'll draw the negative values in green here. Goes down to negative 1 at 3 pi over 2, and then back to back to 0 at 2 pi. Okay. All right. Now, again, this is not a polar graph. You might be looking at it and say, oh, that looks exactly like our graph would look in the xy plane. And that is correct. Right? So this r-theta plane is a plane that we have in, it's a rectangular system. I want to use this to help me graph it in the polar system. Right? So here, down here, I'll have my polar graph. Okay. So again, if we start off as theta increases from 0 to pi over 2, our value of r also increases, right? From 0 all the way up to 1 till we get to pi over 2, right? Again, pi over 2 being 90 degrees, right? So we have something where it increases till it gets to 1 at pi over 2, right? And then what happens here from pi over 2 to pi, the value of r, right? R is the vertical, it decreases to 0. So when I get down to pi, right, in a very similar way, right, almost reflected across here, that value goes to 0. Now, what happens in the green part here of our graph, right? So normally we would expect here the graph to go down from pi to 3 pi over 2 here if the values of r were positive. But the values of r, they're not positive, they're negative. So what happens to this graph here is it gets reflected across the pole, and essentially it kind of retraces these steps, right? Because it has the same shape here, right? It looks like that. So we are actually done with the graph, right? The polar graph is this here. Because once we get to this part here, right, normally we would expect it to look like this, but since the values of r are negative, they get reflected across the pole. So we really just get this circle here. That is, again, different from our previous circles that are r equals, because this one is not centered at the pole or the origin, right? It's off-center. Okay? All right. So in the next few videos, we'll look at different examples a little bit more involved, right, where we'll use this r-theta plane, right, and we use this graph to help us graph it in the polar system. All right, thank you.